All right, so let's see. What are we doing here? Few things. So why do we care about this? I guess guessing you guys are mostly aeroastro folks and you care about things like this. But I would say from a big picture, spacecraft engineering perspective, this like ADCS is kind of one of the core, kind of disciplines within spacecraft engineering. It's important. Almost every spacecraft has to kind of deal with, what parts of the spacecraft need to point where and how well do you have to do that. These are very key, and they're tied to basically every other subsystem, right? So you have to point solar arrays, so it's tied to power, it's tied to thermal, for similar reasons. Propulsion, right? You have to point your engine in the right direction to get your thrust vector where you want it. Telemetry command, right? You have to typically point antennas at ground stations within certain bounds. And then most of the time, our payloads, often are things like imagers need to be pointed as well. So it feeds into basically everything. And these things in turn kind of give us requirements on, these two. So it's important. And I would say also like there's a long history in the aerospace industry of the ADCS or GNC people kind of rising to leadership roles in the projects, which is kind of interesting as well. So it's important. So I'm gonna do kind of a little historical fun, overview thing to warm us up. So this is Sputnik. Everyone knows about this. This did not have any ADCS. It was a tumbling ball with little antennas on it. But very shortly afterward, when the US tried to do its first spacecraft, this is Explorer 1. Does anyone know the fun and fascinating story of Explorer 1? Yeah?
It's one that was they're trying to spin it in some axis,
Yeah.
and the other way because of the and just
Kind of, sort of, yeah. So the story here is this was like one of the first US satellites. It's long and skinny because rockets are usually long and skinny. So it'll become a recurring theme. And they had the great idea of spinning it, which has been done forever on rockets, right? You spin stabilize the rocket, you spin it about the thrust axis. And the idea is that that's going to kind of average out your errors, your alignment errors of your thruster, and that does good things. So they did that. This guy came out spinning about this long skinny axis, but then very shortly afterward, when it got to orbit, it went into what's called a flat spin. So it started doing this, and then it ended up tumbling and kind of spinning the other way. And at the time, this was a huge mystery, and no one knew why. And this prompted kind of the first rethinking, reanalysis of classical rigid body dynamics, and kind of slightly tweaked our understanding of classical physics in a way that like hadn't really been thought about since Isaac Newton. So it turns out that, and we'll get into this in the class, basically, naively, spinning about the long skinny axis is stable, but in the presence of energy dissipation, it is not. And this guy, if you can see, there's these little floppy antennas sticking off. Turns out there's some dissipation because of the floppy antennas. Typically, this is floppy appendages and or fluids, like things in fuel tanks, lead to energy dissipation. Turns out in the presence of energy dissipation, the spin about the long skinny axis is not stable. And the flat spin, sort of the pancake spin, is an energy minimum. So it's a globally stable equilibrium that kind of over the long term, everything settles into. So we'll do this in class, but Explorer is like fascinating because it's one of these very early things, and it kind of forced everyone to really think hard about attitude dynamics. Okay, so now we talked about sort of spinning satellites. SynCom, anyone know what this is? So this was the first GeoComSat. Famously, it relayed the 1964 Olympics broadcast. It was the first time people got to watch the Olympics live on TV because they relayed the TV signals around the world via this satellite. Interestingly, it was also spin stabilized. And if you notice the shape of this guy, what does it look like? It's short and fat instead of long and skinny, right? So they spun it this way, and because it's short and fat, it looks like a pancake, and now that's a stable spinning equilibrium. So that's good. And the idea here is you spin the thing, and then it stays inertially pointed because of conservation of angular momentum. So this is like exploiting passive physics to stabilize your attitude, right? The annoying thing about this, though, so we figured out, okay, long skinny spinning things not stable, fat pancake spinny things stable. Great. Why don't we build flat pancake satellites? This is annoying for a very sort of common sense reason. Rocket fairings are long and skinny. So we figured out we could build fat pancake satellites, but those don't package super nicely into rocket fairings. Rocket fairings tend to be long and skinny, so we want to build long, skinny satellites. to best take advantage of the space on the rocket. So this is kind of the next evolution in that story. TACSAT. So this was the first of what are called dual spin spacecrafts. The idea is, well, we want to build longer, skinnier satellites to take better advantage of the payload volume in the rocket fairing. If we spin that, though, we know from Explorer this is not stable. So a clever guy named Tony Iorillo, who eventually rose to be the CEO of Hughes Space and Communications, which was at the time the biggest spacecraft, commercial spacecraft built in the world. Um, when he was a junior engineer, I think he was like 27 at the company, he figured out that if you, instead of spinning the entire long spinny spacecraft, if you spin only a pancake-shaped part of that spacecraft, and then despin, attach the rest of the spacecraft to that fat pancake part, that you can make that stable. And there's some conditions on energy dissipation. Basically, you can't dissipate the energy in the spinning piece, but if you spin a pancake-shaped piece of the spacecraft and then you do your energy dissipation in the despun part, that is stable. So then they started building satellites that look like this, that took advantage of the fairing volume, but would then despin a chunk of the spacecraft so that you could also inertially point antenna arrays like this. So that was kind of a big deal. And for a long, long time, most satellites looked like this. They looked like this kind of dual spin configuration. There's a huge literature on how to control these things and weird things that can happen where they can get stuck in flat spins and things like this. So that's the dual spin thing. This is a fun historical story. Anyone know about Corona? This is really, really fun. So this it's fascinating. You should read about this. There's actually a bunch of declassified reports on the Corona program. This was the first spy satellite program that the US built to go spy on the Soviet Union. It started in the late 50s and kind of went through the 60s and into the early 70s. Really, really amazing, really fascinating. A bunch of the reports, and there's actually like basically a book that the NRO put together in the 90s, and then it was later declassified that you can get online. Highly recommend checking it out. There's also a mini documentary that the NRO made internally that was classified for years, but got released in the late 90s or early 2000s. Super cool. This was the first spacecraft to do almost everything. So the reason we're talking about it was the first three-axis stabilized spacecraft. So it didn't spin. It had a full three-axis attitude control system that could point cameras at the ground to do imaging. This was also before we had computers. So how did they do all this? The really crazy part of this is what this picture shows. So this was pre like CCDs. We didn't have digital cameras. So how did we get the pictures down? So they used film cameras and they took the pictures and then they dropped the film at the end of the mission. They would drop the film canisters down in a little reentry vehicle that would fall through the atmosphere, pop out a parachute, and then they would go grab the film canister out the back of a cargo plane in midair. They would snag the parachute lines and pull it into the plane. And this became this cat and mouse game where the Russians would also know where these were coming down. So they would go hang out in their submarines where these were coming down in case the cargo plane missed so they could grab them. And then what they did to counteract that is they put salt plugs in the reentry capsule. So when they hit the water, the salt would dissolve and they would sink. So the Russians couldn't recover them. Really, really fascinating. So not only was this the first three-axis stabilized spacecraft, this was also the first reentry vehicle. These film canister entry capsules were the first things that were successfully made to re-enter the Earth's atmosphere. Super cool. They did a bunch of awesome stuff on this. Really awesome. You should check out the weird little internal documentary that still has a bunch of redacted, blanked out things, and the book is cool. Okay, that's Corona. So the first three-axis stabilized commercial spacecraft that sort of like this is now what a modern satellite looks like was Intelsat 5 that was launched in 1980. So this is kind of what arguably modern spacecraft look like. It's got a bus that has inside it reaction wheels. So these are momentum actuators. It's got computers. It's got start trackers. It runs a control loop to. It has a Kalman filter, right, to figure out its attitude, and then it runs a feedback controller to stabilize the attitude using active control through the wheels to then go point the solar rays at the sun, point the antennas at the ground, etc. So this is kind of when computers got good enough to do all this in real time. There's also so why do you think this was? Why did we want to go this way as opposed to the dual spin thing? Like what drove this innovation, let's say? I don't have any thoughts on that. No, no ideas.
Tie gate antennas.
High gain antennas, kind of, not really actually. So those dual spinners had big antennas. They could do huge high gain antennas on the D-spun platform. It's actually these guys. Yeah. So what this did, so the dual spin spacecraft had body mounted solar panels and they were spinning. So only some fraction of the solar rays were ever exposed to the sun, and you just couldn't generate that much power. So as the demand for transmit power on these comsats went up and up and up, the only way to get that was to have these large deployable solar rays. And then these are gimbaled. So you could point the antennas at the ground and then separately gimbal the solar rays to keep them oriented at the sun. So this gave you like an order of magnitude more power than you could generate on just the body panels on the dual spin spacecraft or on spinning spacecraft. So that was the main driver, was power. Okay, and this is kind of the modern era in terms of spacecraft design and attitude control, kind of from the 80s to now. But I would say that is not the whole story. There's still lots of examples of weird spinning and other funky attitude control schemes. So in particular, spinning spacecraft not dead. The Juno mission in 2011 that was launched in 2011 that went to Jupiter was a spinner. And even in the modern sort of like, CubeSat era, there have been spinning CubeSats. We've done them. This is actually an MIT mission that was launched in 2018 that was a dual spin CubeSat. So these kind of weirder ideas still do come back. They're actually all the kind of spinning dynamics and stability ideas that we're going to talk about in here are still extremely important because they're still used during things like thruster firings for orbit raising. Typically, you put the spacecraft into a spin because it stabilizes everything passively and helps, again, average out pointing errors. Also used in safe mode kind of situations. So typically, while spacecraft will have an active control system that's trying to point everything, keep the solar rays pointed, if anything goes wrong, they often have a passive safe mode that they will revert back to, where they put the spacecraft into a stable major axis spin with the solar rays passively oriented towards the sun so that the spacecraft maintains power positivity and stays alive. So these things are still important. They're still widely sort of used, and you got to understand them. Okay, and then just as a fun kind of like intro to me and weird things that we've done in the lab that are relevant here. Let's see. So projects from our group from the last, like, I don't know, 5, 6 years. This is KickSat, which is my sort of PhD project where we built a bunch of these little chipsat things and then flung them out in low Earth orbit. That's the artist rendition. That's the actual deployment. And the idea there was to spin the CubeSat about its minor axis, actually, and deploy these guys such that they came out as sun-pointed major axis spinners. So the little chipsat things were passively oriented at the sun. That didn't quite work out in practice, but got a couple papers out of weird Lyapunov-based control laws to do this and stuff, and it still looks cool. Let's see, we've done a bunch of work on magnetorquer only pointing for CubeSats. So this is like showing one of these slew maneuvers that you can get if you don't have wheels and you only have magnetic torque coils to play with, which is a common constraint on small sats. And then this is a mission we flew last year called Pi4. We had 4 CubeSats where we actually demoed some of these pointing techniques and did sun pointing just with the torquer coils. That's actually actual on-orbit data of the sun vector and showing, turning the controller on and having it spiraling towards the sun. Interestingly, a former lab member who's been working at a company called Albedo, actually Fausto worked at Albedo as well, but if you guys have followed any of this stuff, they're a VLEO startup. They had a reaction wheel failure on their mission, and they implemented a magnetorquer only pointing law very similar to the stuff that we've done in our lab, and it saved the mission. Does it pretty satisfying. They just released a paper on that. Kind of cool. And then I'll mention too, on the hardware side, we've done other weird things with momentum control stuff. So this is a weird pancake motor, PCB motor reaction wheel that a student built in our lab last year that I eventually would like to stick in a CubeSat. And then this was a fun project where we built a reaction wheel backpack for a quadruped robot so it could balance on like 2 feet or 1 foot in theory, and used it to do balance beam walking and stuff like that. So there are other uses of momentum actuators as well. Okay, I think that's sort of the fun stuff, historical overview, weird things that we've done. Some class stuff. So this is kind of, I think, the rough order of like topics that we're going to kind of go through, and we'll start here today. So we're going to talk about like attitude in general, parameterizations, a little bit of like group theory for dummies kind of stuff, because I'm into that. We're going to talk about rigid body and gyrostat dynamics. This is just modeling the physics. We'll talk about digging a little deeper into the physics, what happens when you have damping and perturbations. and how to, deal with that. We'll talk about spinning spacecraft, kind of the explorer stuff and some of the stability ideas there. So that's kind of all dynamics and passive stuff. And then we'll get into attitude determination. So we'll talk about sensors, kind of the very, very classic algorithm for doing this, and then kind of more statistical estimation stuff. So we'll talk about kind of batch least squares methods for doing this, famously called Waba's problem, if you've heard of that before. Has anyone heard of Waba's problem? Okay, 2 people. Awesome. That is the least squares problem on SO3. It's the least squares problem for attitude determination, which is fun and cool and has some almost closed form solutions. We'll talk about Kalman filters. Has anyone written a Kalman filter in here? Hopefully like a few. Okay, so in that case, I'll probably derive the Kalman filter from scratch too, so that we're all on the same page. Then yeah, kind of a bunch of fun, clever, passive attitude control ideas like gravity gradient stabilization, ideas like that. Then we'll talk about active control methods, feedback control for doing 3-axis pointing, that kind of thing. We'll talk a little bit about calibration, which is a big topic. So like, you launch the spacecraft, none of your sensors are all kind of variously misaligned. You don't exactly know your inertia, all this kind of stuff. So how do you calibrate these things on orbit to get better performance? And then, yeah, we'll have kind of an assortment of case studies, and I'm also open to requests. So if anybody wants to hear about anything in particular, especially like later in the course, there's room in there for like deep by default. I'll talk about some case study stuff, but then I think there's also, if anyone has any particular interests, we can do a lecture or two on random topics that people are into. Okay, questions about that? What do I do with that? Okay, that's what we're doing. What is happening? Okay, I think we're still alive. The screen share crapped out. But we're still in there. Okay, grading. There's gonna be homeworks every couple of weeks. That's gonna be like 40% of the grade. There's gonna be a final project, also 40% of the grade. That will be largely based on questions from the homework. So the homeworks will have like a couple, like do some exercises, whatever, and then they'll have like a project question. And the final project will be basically like compiling those project questions and then kind of, I don't know, expanding on them a little bit. So I will basically force you through a bunch of the project throughout the semester. There'll be quizzes. These are going to be pretty chill. They will be kind of short multiple choice things. They'll go out at the end of probably, I think, end of class Thursday, and then like you'll have like a day to do them online. There'll be like an online thing. And then yeah, 5% sort of fudge factor for participation. I think roughly that is, if I know your name at the end of the semester, as in if you've shown up or talked to me, I think that's roughly how that'll go. So if I never see you, and I don't know who you are, it's not a very big class. So I think that's kind of what that's about. So, you don't necessarily have to show up every day, but you should at least talk to me at some point. Okay, cool. And then yeah, so the homework idea, there's going to be some stuff in there that's kind of project oriented. The idea here is you're going to kind of pick a mission or spacecraft or something like that, and then work through a bunch of the design and analysis for the attitude determination control system. So we'll have you implement the dynamics, implement like a full up sim, implement attitude determination methods, implement control methods, like all the stuff. Cool. Any questions on that? Yeah. There's not like a hard attendance requirement. Yeah. And I'm going to post the lectures on, they're getting recorded and they'll be posted on YouTube. So I'm going to post the video recordings on YouTube and all the notes on a GitHub repo. So everything's there. You don't have to show up every week. Life happens. It's not only a graduate course. We're all pretending to be adults. That roughly summarizes. Any other questions on this? Yeah.
You have a policy on listeners.
On what?
Listeners.
Listeners.
Like auditing.
Oh yeah, you can show up. Yeah, I don't care about that. Yeah. Yeah. Okay, cool. Anything else? Okay, cool. Let's see. Other random logistical things. There are several books on this topic. There's several. There's not that many though. I think this is roughly all the books on spacecraft attitude determination control that exist. There's maybe one or two other more obscure ones, but these are kind of the main ones, the classics, so to speak. We're not going to require. So here's something you will find in this field is that it's a terrible mess in terms of notation conventions and things like this. And especially once you start talking about quaternions, there's like a million different ways to write them down. There's a million conventions on how to convert them to rotation matrices, and if it's body to inertial or inertial to body, it's a giant disaster. So you can't trust anything you read. Never sort of blindly implement algorithms out of papers. You basically always have to rederive the stuff from scratch. And to that end, we're kind of have our own set of conventions, and these books all disagree with each other. Some of them even disagree with themselves from chapter to chapter. It is absolutely infuriating. So because of that, we're not going to rely on any of these. We're going to kind of do our thing in class. We'll have our own notation, our own set of conventions that I think are reasonable, and we're going to stick to that. You're very welcome to refer to these. I'll occasionally suggest like sections from these books to read. I have all of these books in my office. I didn't carry them because some of these are big and heavy, but you're very welcome to borrow them, my copies if you want, or you can find them, library, etc., or online in various. So like just a kind of a quick rundown on what these are about. The Hughes book is dynamics. It's kind of all of the kind of rigid body, flexible stuff, damping, all the dynamics content. That's a good spot for that. This book is this guy actually used to teach this course here, and he's a kind of consultant who's done a lot of missions over the last 20, 30 years. So it's very like engineer, nuts and bolts, practical, kind of stuff. So very good if you care about, I don't know, like the details on sizing actuators or sensors for particular kinds of things. This book is by my PhD advisor and a couple other folks. I think this is probably the best reference for what are called control moment gyros, which are a particular kind of actuator that have lots of quirks. So if you're into that, this is a good reference. This is Mark Lee and Christitas. Mark Lee is one of the legends of this field who kind of like invented a bunch of the early stuff. It's a good book. It's more recent and like fairly up to date. Good reference on, particularly on like Pauli filters and things like that, gravity determination. And then this one, the Wirtz book, is the absolute kind of OG classic. It's from 1978. It was the first book on this topic, and for decades, the only book. And it's still a good reference, but I would say it's maybe slightly dated. I think that's the summary. So those are all the books. Refer to them. I might tell you to refer to them occasionally. You can borrow them from me if you need to. But we're not going to really use any book for the course in general. Okay. Assignment 0. There's a course survey. You can do that if you want to. You don't have to do it right now, but feel free to if you want to. It's like a Google form with a handful of, it'll take you 5 minutes or less. So feel free to do that. We'll leave it up for another sec if it needs. Okay, cool. So that's that stuff. Quick, like logistical sort of stuff. So throw this over here. Hopefully this works. Okay, great. Things are still working. Okay, so we have a Canvas. How many people are already on this? Not that many. Okay, cool. So check this out. There's a whole bunch of like to-do items here. First of which is that course survey thing I just gave you the link to. There's a Piazza, so let's look at that, that you can join. That's the next thing. So Canvas will be used for assignments, basically. So I'll throw the assignments up there. We'll use that to kind of like, I don't know, submit assignments and grades. Piazza is, I think, what we'll use for any kind of discussion, homework questions, etc., and announcements. So I guess we'll go through these things. There's a syllabus, there's YouTube and GitHub for lecture stuff. So let's see. There's the survey. Hopefully you can find that. It's pretty quick. Piazza. So there's the same information duplicated here as an announcement, but this is what I'll use to like put out announcements and then for like homework questions, whatever, post them here. Then we've got GitHub for, oh, here's the syllabus, right? I think I already kind of walked through all this stuff, but you should check it out. In particular, we're going to have office hours. I'll have office hours every week. I was going to put out a little schedule poll to figure out what is the least conflicted times for that. Homeworks, we're going to have like 4 or 5 of them, and they'll be every 2 weeks. I haven't figured that out yet. So they'll be due on some particular day that should be consistent. Quizzes we talked about, Piazza, blah, blah, blah. We kind of talked about this stuff. There's the books. There's kind of, stuff we already talked about. Oh yeah, late homework. I'm relatively lax about this, but I think the gist is, we should probably close that. Thank you. I think we'll have like a late day budget. I said 6 days or whatever. So the idea is I don't want to have to like police this or think about it. So there's a late day budget. You can use them in any combination you want. Uh, please don't abuse or go past that. If you have a life situation, it's okay. Let me know. We'll be reasonable. But yeah, I don't know. I think that's that. And then yeah, this is kind of the topics which we already talked about. Spring break in here. I have to go to LA this week, and I'm gonna try to hook up someone, potentially Michael Palushik, the guy that wrote the first book who used to teach this class. He has a lot of good war stories to talk about kind of sort of war stories of doing cool things on missions. I think that's it. Any questions about logistical things? Oh yeah, we have a YouTube channel that I finally managed to set up. It's really hard to transfer YouTube channels, it turns out. It's quite difficult, but I figured it out. It took like an inordinate number of hours. But this is going to be, so videos will get posted here kind of after class. And then this is the GitHub. Right now it just has the syllabus, but I'm going to post the lecture notes, like PDF of all the notes in here as well. Okay, I think that is all the logistics. Any comments, thoughts, questions? Everybody cool? Excellent. All right. That's that. Now we get to actually do stuff. Now I have to figure out how to not like, oh, it's my email. That is weird. We don't want that. We want this. Okay, great. I think I'm gonna have to like pull up a chair for this. I don't think I can punch over on this thing for like another hour. This weird, awkward position. Uh, right. That's convenient. Okay. Yeah, something. So annoying. Okay, here we go. Yeah, I'm gonna pull up a chair. Sorry. You're doing that, but I'll try to get some kind of box to prop this on for the future. And of course, right on schedule. Okay, we're still there. It's not gonna die on us yet. It's gonna work. Okay, let's just get all of this. Okay, cool. Let's do it. Hopefully we can make this work. Now I have to get my notes up. All right. So first topic for discussion, and question for the audience. What is attitude? Anyone want to give me a definition? Can be practical working definition or mathematical definition. What you got?
It's just orientation of the body.
Yeah, it is orientation of a body. That's a good start. How do we like define it precisely mathematically? Anyway,
So we're just going to add relative to a reference frame.
that's it. Yeah. So that's like I think the core. That part is the core like slightly tighter definition. So for us, this is going to be the relative rotation between two reference frames. And typically, this is some sort of body frame attached to the spacecraft, which we make up, right? So some kind of spacecraft body frame, and then some kind of inertial frame, which also we get to make up. And this is typically mission specific. For Earth orbiting missions, it's typically some kind of ECI, like Earth-centered inertial coordinate system. But if you're not in Earth orbit, that doesn't make a whole lot of sense. So it can be a lot of things, and it tends to be mission specific. Also, just for the record, right? It's also not usually inertial, truly, right? Like ECI isn't actually an inertial reference frame because it's attached to the Earth and it's moving. And these kind of very subtle points do come up when you start to do really precise stuff. So all of this is kind of hand wavy and approximate if you really dig in. Okay, so that's kind of practically a working definition. It's a rotation between two reference frames. One of them is some sort of inertial frame, and one of them is some sort of body frame that's bolted onto the vehicle. And then if we go like one step more abstract, and we'll talk about this, this is a Lie group. Has anyone heard of this before? Nobody? Cool. A little bit, maybe. All right, we'll do a little of this. This thing's called SO3. We'll talk about it. All right, so that's sort of some definition stuff. Now we got to do what is a reference frame? So, I want to take a stab at this one. All right, so we'll just go with this is a set of mutually orthogonal basis vectors that we're going to choose so they're ordered to make a right-handed coordinate system. And you will find a lot of this stuff is like arbitrary and deeply arbitrary, and they're just conventions. I think this pervades this, and which is why it's such a mess from a notational perspective. And a lot of the references is that it's layers of arbitrary conventions, and since the choices are arbitrary, a lot of people make different choices, and so you end up with like a real mess in the literature. Okay, and then I would say for our purposes, um, a reference frame and a rigid body go together. So these are like sort of synonymous. Roughly speaking, reference frame is typically referring to like the kinematics of this stuff, and rigid body refers to the dynamics, but they're kind of a package deal. Okay, and then from a reference frame perspective, we'll primarily deal with two kinds. We're going to have so-called inertial reference frames, also referred to as Newtonian reference frames. And what that means is that F equals ma holds from a practical working perspective. That's actually never exactly true, right? Like the Earth's surface is not really an inertial frame, right? You can do easy, cheap experiments to verify that it's not, like a Foucault pendulum. Has anyone seen those before? Those are really fun. So we're not an inertial frame. ECI is not really an inertial frame. Like there's really no such thing, but the idea is if the residual on F equals ma is tiny, then this is a good approximation and works in practice, right? But what tiny enough is application dependent. Okay, so that's inertial. And then the other one is we're going to call like body fixed or just body. Which is attached to and rotating with a rigid body. Okay, any questions about that? Good so far. Excellent. Okay, so a lot of this is like hopefully very, very sort of familiar things you've seen before, but we got to sort of make sure we're on the same page. So vectors, talk a little bit about vectors in a very pedantic way, because we're going to end up talking about sort of how to transform vectors between coordinate frames and stuff a lot. So we have to be a little careful about definitions and how we talk about these things. By the way, if my handwriting is bad, I apologize. Speak up. Yeah. Okay. So we're going to distinguish pretty strongly here between like an abstract or like physical concept of a vector and coordinates that you write down in like an array. So we'll talk about like physical or abstract vectors. Um, that exist sort of independent of any coordinate frame. Okay. And like these are useful for, I think, conceptual thinking, but you can't calculate with them, right? So to be clear, right, what we're talking about here is like, freshman physics cartoon, little arrows, right? So there's an arrow somewhere hanging out in space. We're going to write this sort of like abstract vector with an underline. Okay. That's what that is. And now, right, we can't calculate with that. It's sort of this abstract thing we can draw cartoons of, but we can't actually compute with it. So whenever we want to perform calculations, we have to choose a basis. And how we actually do that, what you're really doing when you write down three numbers for a vector in R3 is what you're really doing is projecting this abstract vector onto some set of basis vectors for the frame you have chosen, right? So there's projection sort of implicit in writing the numbers down. Let's see. So we project V onto a set of basis vectors. Um, and write down its components, which are literally the dot products of V with the three basis vectors. So, okay, so let's do that. So we have this like abstract vector V with the underline. And if I want to write this down, I can write this down a couple ways, right? So I can write it down as so we'll embrace this idea of like Newtonian or inertial frame and body frame, and we'll kind of write it both ways. So this is this abstract arrow hanging out in space. I can write it in components in, say, an inertial or Newtonian frame. So that'll look like this. So I'll have V1 in the Newtonian. So when we'll use N for Newtonian or inertial frame and B for body frame. So we're going to have this situation. So I've got sort of three components that are along three basis vectors. And I can write that in a fun, compact way that is a little weird, but I kind of like this. We'll write it like this, which is, I mean, this is sort of trivial, but I can write this as like a little, inner product type thing. So this is cartoony math, but this thing down here, um, maybe I'll move this actually to the next page. So we're going to call this sort of thing, and this sort of emphasizes that you're doing this bunch of dot products, right? You're like projecting this thing. Um, this thing is sort of your components on the right, and then this thing on the left, we're going to call this a vectrix. So it's like a matrix of basis vectors. And remember, these are like cartoony abstract things. They don't have numbers attached, right? So I can write it this way. I can also write it equivalently in the body frame. So I'd have now the body components, and we're going to write those basis vectors as B's. Uh, all right, and I can do the funny little vectrix thing again. This vectrix notation is from the Hughes book, by the way. I don't know. It's somewhat popular in like aerospace circles, and I kind of like it for this kind of stuff, but it's not super common. If you're weirded out by it or have never seen it before, it is kind of strange. So this we can write this little. So what we'll do now is we'll kind of abbreviate this as the vectrix that is the full set of those basis vectors. We'll write like that, and we can kind of write this as kind of this uh, array of components. So that's the set of basis vectors, and then this is the components. And maybe we're going to call this thing vectrix, and then this thing is sort of component matrix or array or whatever. Okay. And then, yeah, I think the main message here is that it's really important to distinguish between like this abstract vector and its components in a particular reference frame. So we're going to have to go between reference frames a whole bunch. And the vector is not changing. That's the important thing, right? The vector is some little arrow in space. The components change, right? But the vector doesn't change. Okay, any questions about this stuff? This is hopefully review familiar. All right. All right. So we got that. Next step. Uh, how do we write down attitude? Like how do we parameterize it? Uh, this one, hopefully folks have seen these things before. Um, let's see. So I would say the first thing to note is that the convention we're going to use in here, which I think is more or less standard in aerospace and robotics, though not universally so, is that um, we're always going to write the attitude as the rotation from a body frame, some body fixed frame, to some inertial frame. So it's always the B to N direction. We're always going to parameterize it that way. That's relatively standardized in aerospace and robotics. In physics, it's often the other way. And in a bunch of random references in both those fields, you'll also find it the other way randomly, infuriatingly. That's the way. But we're going to do this. I think this makes a lot of sense because if you're sort of designing control algorithms, if you're thinking about, you're flying in the vehicle, you're driving the vehicle, whatever, all your sensor information is coming in the body frame. And this is sort of the natural way to do it if you're in the vehicle, I would say, right? Uh, Whereas if you're a physicist and you're like looking down at the experiment in the lab frame, maybe it makes sense to do it the other way. But we're going to go this way because we like to ride in our spaceships and stuff, right? Okay. This is not universal, right? We already talked about that. Um, yeah. Okay, cool. So that's how we're always going to do body to inertial in here. Next question is like, how do we write these things down? So things people have seen in the past. How have you dealt with writing down rotations before? Euler angles. Yes, that's always the first one that people talk about. And these are evil and terrible and bad for you, and you should never use them again. We'll just get that out of the way right now. The classic way to write these down is roll, pitch, yaw. But like all things in attitude, there's literally 27 possible conventions for how you can write these down. You can change the order up. It can be inertial to body or body to inertial. It's a giant mess. So never ever trust any code you find. Never ever trust any papers you find. Rederive it yourself every time, et cetera, et cetera. Okay, so I'm going to straight up say you should never use these. End of story, full stop. Never. They never have a good use case. It's a terrible sort of travesty of history that these are the first thing that we teach undergrads in intro physics, but they're literally the worst possible choice that you could make in almost every case. I can't overstate how terrible these are. Okay, so we're gonna go with that. So we're gonna just kind of do a little pro con thing now. These are a minimal parameterization. So they have three numbers. Uh, and they're intuitive. I would debate that, and I think there are other options that are equally, if not more intuitive, that work better. So, con, many cons. They have singularities. Who's heard of this before? Okay, can anyone tell me what we mean by singularities here?
Oh, it's just me.
I don't know, there are a couple people, but you're in front here, so you were here late, so you get to pick on.
Um, it's a like gimbal lock where you can have things oriented in such a way where you can't necessarily solve the equation.
Yeah, that solve the equation thing is getting at it. Do you have another version?
You like a sine or cosine, and you have like zero, but then you're dividing by it.
Yeah, so that divide by zero thing is kind of at the heart of it. So what ends up having specifically the mathematical thing is related to what you just said, this idea of a mathematical singularity. So what it really is if you write down the Jacobian matrix associated with mapping Euler angles into something else. So it could be the conversion between, Euler angles and angular velocity, like the derivative kinematics, or it could be the mapping between Euler angles and some other parameterization, whatever it is, or the rotating of some vectors or whatever. That Jacobian has points where it becomes singular, i.e., not invertible or divide by zero kind of stuff happens. This is literally crashed vehicles. It's terrible. Never do it. Typically, these go singular at 9. The standard roll pitch yaw ones go singular at 90 degrees of pitch is a classic one, but it's basically where some trig function goes to zero. And in some Jacobian somewhere, you're going to have a singular Jacobian that's not invertible, or in some code, you're going to have a divide by zero error because of this. So typically this happens at 90 degrees. And these things, if you ever try to do, kinematics, any kind of integration, these are all of the functions involving these are a mess of trigonometry. So there's like all kinds of nested sines and cosines, and it's really terrible. Also similarly, right? Has anyone ever had to try to like add two rotations together in Euler angles? Awful, right? Don't do it. Okay. Hopefully I was clear. We will not be using these in this class. Should stop now. Okay, so anyone have any other ideas? Those are good. Let's save that one. We'll get there. I mean, we can do it now. What the? Yeah. Yeah. So that's like the other classic choice that you learn about in like freshman, physics, mechanics, whatever. Um, Rotation matrices, which we'll spend some time on. So these have some good things going for them. In particular, these, unlike the Euler angles, these are globally non-singular. They never go, there's no weird, non-invertible matrix stuff. The kinematics are well behaved, et cetera, et cetera. They're non-singular, so that's good. It's easy to rotate vectors with these. We all know how to do that. Unlike Euler angles. And it's easy to compose rotations, right? If I have rotation 1 followed by rotation 2, I just multiply the rotation matrices. Super easy. So I guess, yeah. Linear kinematics, composition rule is nice, stuff like that. Cons with these are that they're highly redundant. So if I have a rotation matrix, there's 9 numbers in that 3 by 3 matrix when this is only a 3 degree of freedom thing, right, that we're talking about. So I have a lot of extra numbers. You might say, well, computers are pretty good now. Why do I care? Multiplying 3 by 3 matrices is pretty easy. That is true. I would agree with that. However, there's a more subtle issue with the redundancy. It's that these things, because it is only a 3-DOF sort of object, it means that if there's 9 numbers for something that only has 3 degrees of freedom, it means there's 6 constraints on this thing that have to be satisfied for it to be a valid rotation matrix. And those additional constraints are a little subtle to enforce. And if you go and use these in a computer enough, in particular, if you go simulate dynamics, if you go simulate like a tumbling satellite with a rotation matrix as the attitude parameterization, very quickly, if you use like Runge-Kutta, like ODE45 type stuff, the matrix that you're using in here will drift because of numerical error, such that it is very quickly no longer a rotation matrix. It'll be some weirder matrix that doesn't satisfy the properties of a rotation matrix, and that's pretty annoying. And it turns out it's sort of non-trivial to fix that. So that's the reason we don't love these for doing dynamics. So 9 numbers for 3 degrees of freedom. That means we have 6 constraints we have to satisfy. Okay, so You already brought this up, so we'll go right to we've got quaternions. And these are sort of a very, I guess, very classic topic in aerospace and robotics. They're very widely used. Also in computer graphics, these are a standard thing. And we'll be doing a very deep dive on these. So I've sort of, for many years, been obsessed with quaternions. I think there's also a quote somewhere that like no one really understands quaternions from some famous physicist, and they are weird. I will do my best attempt. I've wrestled with these for many years. I have strong opinions on them. Uh, and we'll hopefully try to like get you to a place where you're not weirded out by them and are like somewhat comfortable with kind of where they come from and stuff. I think we'll get there. So pro on these guys, they are also non-singular, like the rotation matrix. It is also to sort of the big pro on the quaternion versus the rotation matrix is so rotation matrix are great for rotating vectors and transforming things and for composing rotations. Quaternions are great for simulating dynamics. This is their strong suit. Uh, the con here is these guys are redundant like the rotation matrix, but they're much, much less redundant and easier to deal with. So these guys have 4 numbers for 3 DOF. So they have 1 inherent sort of implicit constraint. Turns out that's much easier to deal with than the rotation matrix case. It turns out the deal here is to be a valid rotation, you just need it to be unit norm. So it's a 4-dimensional thing that has unit length. And that's really easy to enforce, right? You just divide by the norm, normalize it, whatever, and life is pretty good. So these are convenient. Okay. There will be much more to come on this. Anyone know about any other ones? Yeah.
Isn't there like that one? Disabled hair.
Yes, this is a very good one. There's a huge library of other 3-parameter ones that are all better than Euler angles. And this is the first one. So we'll do this one. This is a good one. And we will use these. So we'll call this actually goes by a surprisingly long list of names, one of which is Euler parameters or something, which is super annoying because it gets easily overloaded with Euler angles. So we're going to not call it Euler at all. We will call this an axis angle vector. Because that's and these are actually very intuitive. I think I would argue these are actually way more intuitive and easier to think about than Euler angles. And I wish that these got taught instead of Euler angles in like introductory courses. So these guys on the pro side, they're minimal. It's only 3 numbers. They're also very intuitive and easy to interpret. So what they are is literally, if you have some rotation, you can always write it down as a rotation about some axis by some angle. So it's literally if you took the unit vector axis that you were rotating about and scaled it by the angle of rotation in radians, that's what this is. So right off the bat, if you look at the direction, it tells you the rotation axis. And if you look at the norm, it tells you how far you're rotating about that axis. Super intuitive and nice. I think these are much, much nicer than Euler angles from that perspective. And then they're also better mathematically. So on the con side, they have singularities. In fact, you can prove pretty easily mathematically that all 3-parameter attitude representations have to have a singularity somewhere. So these guys do have a singularity, but where the Euler angles have the singularity at 90 degrees, these don't have the singularity till 180. So I would argue they're just universally better. And there's also other choices that are similarly good. So this is one choice to use when you need a 3-parameter thing instead of Euler angles. There's another fairly common 3-parameter choice. Anyone know any other ones? Okay, so another good one is called sometimes called a Gibbs vector or a Rodriguez vector, Rodriguez parameters. So Gibbs slash Rodriguez vector or parameters. These are very similar to the axis angle. They're just scaled differently. So basically, instead of being like the length being the rotation angle in radians, it's instead it is the like basically tangent of the rotation angle. It's scaled by some trig stuff, um, which sounds weird, but it turns out it's convenient mathematically. So the kinematics of the axis angle vector are kind of nasty and involve either trig functions or exponentials. These have polynomial kinematics, which is nicer to deal with in a lot of cases. So these are extremely common in practice. In practical applications, I would say these are probably the top choice over both Euler angles and sort of axis angles when you actually need to do computational things with a three-dimensional representation. And then con on these guys, they have singularities. So just like the axis angle stuff, they have a singularity at 180, but they also, it turns out there's a trick you can play um, where you can push the singularity out arbitrarily far. So there's another common variant on these called modified Rodriguez parameters that push the singularity out to 360, which is kind of cool. So there's always got to be one, but it turns out with these guys, there's this kind of trick where you can kind of push it arbitrarily far out. And then there's some other tricks you can play where you basically switch between parameterizations. You can think about it as basically like switching the reference that you're rotating from by 180 such that you never hit the singularity. So you can basically, for the expense of having sort of some switching logic, you can always use the three parameter set and you can always guarantee that you won't hit the singularity. All right, cool. Questions, thoughts? Everybody cool? Okay, so we're going till 2, right? All right, so that's good. So we got through some, I think we have time for some more fun. All right, so that's like survey stuff. I think what we'll do now is we'll start digging in a little bit into rotation matrices. All right, so I think probably everyone has seen these before. So let me know if this is not, stuff, but hopefully we can go pretty fast through this stuff. So again, we're going to always transform from body to inertial with these guys by our conventions. All right, so in components, we're going to write it like this. So we've got some V here, and this is in the N frame. So this is a little array, right, of 3 numbers that are written in the inertial frame. And we can write this like so. So we're going to use capital Q for rotation matrices, little q for quaternions in here. Yeah. Oh, yeah. This is what happens when I try to write and talk at the same time. They're not always coordinated. There we go. Thank you. All right, so we're going to write this with a bunch of decorators that will just for like we're going to be a little pedantic for now and like be extremely explicit about everything. We're going to drop a bunch of these superscripts because eventually, but for right now, I think it's useful. So left superscripts on these little guys means that they're arrays of 3 numbers of components in that frame, right? And so, and then the rotation matrix is always going to be from body to inertial like that. So we're going to drop the upper subscript, superscript N and B's on the rotation matrix because we're just always going to assume it's body to inertial in here. But for now, we'll kind of be a little bit explicit. And then we can think about this a couple ways. So back to our little like vectrix notation. So this is kind of abstract vector V. I can write this kind of 2 different ways. So I've got all my N basis vectors over here. And I've got my N components over here. And I can also write it equivalently as the B basis vectors and like the B components over here, right? Oh, yeah. You can yell at me for bad handwriting. It's okay. I will clarify. Transpose. Yeah, sorry. If it's really bad, I'll try. But hopefully it's mostly interpretable. I'm going fast and my handwriting is not good to begin with. If there's issues, let me know. I'll clean it up after too. I can clean it up on the PDFs after class. So definitely let me know if it's
It is T for transpose.
it is T for transpose. That is correct. Okay, so we got this, right? So I can write it both ways. So what I'm going to do now is play a little trick. So I'm going to write this line with this weird vectric stuff real quick. So I can write, so in the end frame, right? Remember, this is the basis vectors dotted with these kind of like, it's V dotted into all the basis vectors, right? So I've got this. So I can write that like this vectrix n thing dotted into V. And now um, I can plug one of these in here. So I'll show you what I mean by that. So I can take n, and then I can replace the abstract V with the body component version. So that's um, body vectrix sort of times the components here. And then if I just regroup this, I can pull the basis vectors out front and then leave the components over here, right? And so this thing, if I just look at this now, I've got VB over here, I've got VN over here. So this thing is the rotation matrix. And this makes it like nicely explicit, like what this thing is. And also someone said I think you said direction cosine matrix. That's where this comes from also. So this thing right here is the rotation matrix from body to inertial. And it makes it super like nicely interpretable what's going on, right? So I've got this thing expressed in the body components, and I'm basically like taking it and reprojecting it onto the inertial frame components. So I can take that and like expand it out now. So I'll use that definition, right? So you can think about it a couple ways. One way is it's basically the outer product of all the basis vectors. I've got like n1, n2, n3, and I've got b1, b2, b3. So if I kind of expand the outer product out, I'll do maybe explicitly once. This is like n1 dot b1, n2 dot b1, n3 dot b1, etc. And so can anyone like now interpret the name direction cosine matrix? What's that coming from? Anyone have any thoughts on that? No. So the direction cosine thing is coming from like these dot products between the basis vectors. The dot product is the cosine of the angle between the basis vectors. So literally what this matrix is, it's a matrix that each component of this is the cosine of the angle between a pair of basis vectors. So I just take all the pairs of basis vectors that there are, and I take their dot products. I take all the possible dot products. This is all the cosines of all the angles between the directions, I guess, is where that's coming from. Okay, so this is kind of fun now. So this is like an explicit recipe, right? So if I have two sets of basis vectors, all I'm doing is this. I'm like taking their outer product, or I'm expanding out all the possible dot products between them. And there's a couple ways to reinterpret this that I think are fun. So one version of this is if I think back to the definitions of all these things, if I now go look at the columns of this matrix, can anyone interpret the columns of this matrix in terms of like something we've already seen? So in particular, the columns go down, all the columns are B1 and then B2 and then B3, right? So each column is like one component of B dotted into all of the inertial frame vectors, right? So what's that?
It's just the direction of the B1 vector in the N1 frame.
Yeah, so that's right. So basically the columns of this thing, what the columns are the B frame basis vectors written in the n-frame components. So this thing is giving you basically like the mapping between the two frames, as in it's telling you what one frame's basis vectors are in terms of the other frame's basis vectors. So if you look at the columns, that is the B frame basis vectors written in the n frames components. How about the rows? You want to tell me what the rows are similarly? If I look down the rows now, it's the opposite. It's n1 dotted into all the B basis vectors, n2 dotted into all the B basis vectors, et cetera, right? So the rows are the opposite thing. They are the n frame basis vectors written in B frame components. So let's write that maybe a little more explicitly. This is body basis vectors in inertial components. And then this is inertial basis vectors in body components. So this thing basically is telling you one frame's basis vectors in terms of the other frame's basis vectors, right? And it sort of like goes both ways. Okay, everyone cool with that? Thoughts, comments, questions? Okay, that's kind of deep and I don't know, kind of cool. Okay, so now from there, I have a question that I think if you're paying attention to that, you should be able to answer this. What is the inverse of Q? Anyone? It's this is really telling it to you right there. Yeah, why? Well, yeah, I mean, you already knew this, is what I'm getting at, because you're not explaining it in those terms. You just know the factoid. All right, so check this out. If I take that, so I've got Q transpose Q. If I write that out, that looks like B1. If I write these out, like in terms of these components, and I could write it either way. So it's these basis vectors times these basis vectors, right? It's all the basis vectors times themselves, right? And what does that have to be? So if I take this outer product of the basis vectors, so I've got like B1 times, dotted into itself, B1 dotted into B2, B1 dotted into B3. So what's B1 dotted into itself? 1, because it's unit vector. What's B1 dotted into B2? Why? Why? Because they're orthogonal, because it's a basis, right? Okay, so basically, this has got to be the identity matrix. Because if I take these guys, dot products against each other, when it's dotted into itself, it's got to be 1. And then when it's dotted into any of the other basis vectors, it's got to be 0 because they're orthogonal. So Q transpose Q is the identity, which tells you the definition of an inverse is that you get the identity, right? When you multiply the matrix by its inverse. So this is telling us right now that Q transpose equals Q inverse. Okay, so this, which someone already said, if you have this property where the inverse is the transpose, this is called an orthogonal matrix. And why? It's because if this is true, that means the columns are all mutually orthogonal, aka the columns form a basis, right? So that's why it's called an orthogonal matrix. All the columns are orthogonal vectors, and the rows are orthogonal vectors, right? It goes both ways. Okay, so that's cool. So we've got this thing, rotation matrices are orthogonal matrices, but that's not the only thing they have to satisfy. There's another property that they also have to satisfy, which is now another fun challenge question. What is the determinant of Q? So let's back up a step. Can anyone tell me what geometrically what a determinant is? Anybody?
Is it the length of the vector?
No. So, okay, how about like for a 2 by 2 matrix? So if I have a 2 by 2 matrix, do you remember how to compute the determinant? So like this way minus this way, right? So if I think about two vectors and I'm doing that, what is that actually giving me? So it's like related to a cross product, right? That's kind of what you're thinking about. But what is the norm of it?
Yeah.
Yes, that's it. So determinants measure in 2D the area spanned by the columns, by the column vectors. In 3D, it's the volume. In n dimensions, the determinant gives you basically the sort of volume scaling of a matrix. So if you think about what the action of a matrix is on a vector, the determinant tells you like how much, it's telling you how much the matrix stretches volumes. And you can interpret it as literally the volume spanned by the column vectors. So it's intimately related to volumes and sort of stretching of volumes, right? So just from like the geometry, all right, so from that kind of idea, and that's the idea of like it's kind of the volume. So the technical word for this is it's giving you the volume of the parallel piped, which is if you took all the vectors of the columns and were to like make a little polygon thing out of them. And I'm not only bad at handwriting, I'm also bad at drawing. So you will you'll have to suffer through this. But if you were to like take the, kind of these columns, and in this case, because they're all orthogonal, it's a little cube, right? So it's basically giving you the volume of this cube. Okay, so what is this volume for this rotation matrix? 1, right? It's just a little box, unit length on every side. Easy, right? Okay, so that is telling us the determinant of a rotation matrix has to be 1 because it doesn't stretch vectors. It only rotates vectors. And if you look at the columns, they're all orthogonal. They make this little cube thing. They're all unit length. It's got volume 1, right? Okay, so determinant 1. So we've got that. Determinant of this thing has to be 1. What about the sign of the determinant? It's possible to have negative determinants, right? You know this. Hopefully, you guys are taking some linear algebra. I don't know, maybe not. It's okay. What does the sign of the determinant tell you in this kind of geometric picture? So we'll skip yeah. No, so if it's less than 1, it's shrinking. If it's more than 1, it's just scaling. It tells you, this volume is a signed volume. So what that's doing really is if you imagine the 2D case and think about like a cross product, it can go this way or this way. All right. And so what does the negative case correspond to? It corresponds to a left-handed coordinate system or a left-handed ordering of these guys, right? So from that perspective, because of our conventions about the world, this guy always has positive sign because we're choosing a right-handed coordinate system. So because of the choice, which is arbitrary, right? Um, we're always going to enforce right-handed coordinate systems. So our rotation matrices will always have determinant +1, never -1. Based on that, can anyone tell me what it would be if I can have an orthogonal matrix with determinant -1? What would that correspond to? Yeah. Yeah, exactly. It means I'm like flipping one of the ordering here of these basis vectors and making it a left-handed coordinate system. If I were to apply that transformation, what it is, it's not a rotation, it's a reflection. Basically means I'm flipping one of them. So I'm reflecting across some plane, right? Okay, so determinant +1 equals rotations. Determinant -1 equals reflections. So orthogonal matrices encompass both rotations and reflections. If I restrict it to positive determinant +1, then I'm just getting the rotations. So fun facts. Okay, cool. So, any questions about that stuff? Well, geometry fun. And hey, now you know group theory. So we'll summarize this in like a little bit of the fancy math terms, but the discussion we just had is basically defining uh, how you define the rotation group in group theory. So we'll just kind of like hopefully finish off today with a little chat about this. So this is a little bit more abstract, um, but I think it's good to know about some of this stuff. So first of all, what's a group? Has anyone done this stuff before? Okay. Do you want to offer some thoughts on what a group is? All right, that's all right. No worries. Okay, so basically for our purposes, every group it's just a group of matrices. Um, you can write them down other ways. They all have but they basically all have matrix representation. So you can always write a group as some group of matrices that satisfy certain properties. And here's what you need. So number one is it has to have an identity element, i.e. identity matrix in the matrix case. It has to have an inverse, and it has to be closed under some kind of multiplication rule. So in the matrix case, this is all obvious. You've got an identity matrix, you got an inverse, so they have to be invertible matrices. And then the last one is if I take any two matrices from this group and multiply them together, I have to get another matrix that's in the group that satisfies the group property. So we call it being closed. So in matrix land, this is all pretty obvious. And you can come up with very easily lots of examples of these things. So let's think of some examples. Maybe I need a new page for that. So let's see. One example, maybe the simplest, most familiar example would be the positive real numbers. So if I take any, two positive reals and multiply them, I get another positive real. If I take the identity element is one, and the inverse is one over the number, right? So that's easy. Interestingly, the full real line, positive and negative, is also a group. But what do you have to do? It's no longer it's not multiplication anymore. It turns out if the sort of binary multiplication operator becomes addition, which is kind of fun. Anyway, okay, what else? So this is a good one. And then so there are lots of kind of group theory in general is all about symmetry. And so usually these groups can be interpreted as like describing some symmetry. So there's lots of examples of what are called discrete symmetry groups. So a good example would be um, the symmetry group of like a polygon in the plane. So like take a square. It's the set of transformations I can apply to the square such that it still looks the same. So that would be all the rotations by like modulo 90 degrees and then all the reflections you can do, right? So it's got 8 elements in the group. You can like rotate it 4 different ways and you can flip it 4 different ways. That's called the dihedral group. And the one for, you write it D for dihedral and then a number. And the number corresponds to the number of sides on the polygon. So for a square, it'd be D4. And it's pretty intuitive to figure out what that is. And in fact, it's actually just a bunch of matrices, right? And it turns out they're closed, right? Because if I take, say, rotations by 90 degrees and multiply them together, I get another rotation modulo 90, blah, blah, blah. So it's closed under multiplication. That makes sense. Okay, what else? Some other ones that are pretty common would be the set of n by n invertible matrices. Right, so that satisfies all the properties. It's not just any n by n matrix, so they have to be invertible, right? So this is called the general linear group of n dimensions, right? N by n matrices. That's pretty easy. Okay, so now we get to rotations. So rotations in general, in arbitrary dimension, it's called the SON. The O is pretty obvious. The O stands for orthogonal, which we just talked about. Orthogonal matrices, orthogonal columns. The columns are basis vectors. The S, anyone know what the S is for? The S is for special. And special refers to determinant plus one. So if it's just O, that's the orthogonal group, which is also a group. And you put the S in there, it means they've got to have determinant plus one. So they can't, it's disallowing reflections. So we're going to deal with specifically with SO3, which is rotations in 3D a lot. Another one that comes up quite a bit, though, in applications, especially in robotics, is the rigid body motion group, which is called SE3 or SE2 in the plan. So this is rotations in 3D plus translations. So this is combining sort of SO3 with, I guess, R3, right, with translations. And it turns out you can write those as 4x4 matrices. Has anyone seen that before? And they kind of compose in the ways you'd expect, right? And they're all invertible. Cool. Okay, so these are some groups. And there's two particular flavors of group here. There's sort of discrete groups that have a sort of fixed number of elements, which would be like the dihedral group there for like the square. So there's like 8 elements. You can count them, right? Versus continuous groups, which would be like rotations, right? So there's some continuous parameters there, like some angles that are, you can't count them, right? There's sort of an infinite number of elements, but there's continuous, right? And so continuous groups, like rotations, are called Lie groups. And that it looks like it might be Lie or something. It's Lie. It's a guy named Sophus Lie, who's I think Swedish. I don't know. That's how you say it. Okay, so that's that. What else we got here? Oh yeah, it's just about done. So this is good. So we got to a good spot. So final fun fact of the day, right, is the group of 3D rotations is called SO3. The S is for special. Uh, and that refers to the determinant being +1 and not -1. And then the orthogonal is what we already talked about, is that the matrix is an orthogonal matrix, which means that Q transpose equals Q inverse, or Q transpose Q equals I, etc. And then the 3 sort of obviously refers to the fact that it is in 3 dimensions, it's a 3x3 matrix. Okay, cool. That was excellent timing. It's like I did it on purpose.